Hello everyone, my name is Nathan, otherwise known as Old Man Builds, and welcome to the Builder's Workshop. We have Shawn Calderon here. We also have the Benny Factor. Guys, we're rocking today. We got some good stuff for everybody.
Oh yeah.
Yeah, I'm totally excited.
So am I. So am I.
So we're going to have Shawn present first. He's got some cool stuff to talk about and some experiments that he's done. Then Ben's going to go ahead and take over. He's got some awesome rodent coil stuff and some good information to go over. So we're going to have a great show, guys.
Awesome. Thank you, Nathan. I'll take it from here. Hey, guys, it's great to see you coming into the chat. And I really want to thank you guys for hanging in there for my Wednesday presentations. It just so encourages me and it just keeps me moving forward in my experiments, looking forward to share them with you guys every week. So I really appreciate you guys. Also, I appreciate the participation of Ben and Gerald and the leadership of Nathan. I just wanted to throw those plugs out real quick. So if you can see the screen in front of you, I have a hand-drawn diagram of what is called the Asaki oscillator. And what I was trying to do is create a sawtooth waveform to input into my Tesla coils to see if I can get some different effects in the plasma. So currently I just input a positive pulsing AC signal, if you will, or a pulsing DC signal to get some of the plasma effects in the ZVS. So I was wondering, what would it be like if I changed that positive DC pulse to, let's say, a sawtooth? And the only ways to do it were to use IC chips. And I'm allergic to IC chips, so I need to keep it simple for me. I stumbled upon this super cool little oscillator. I played with it. I didn't do a whole lot with it, but I thought it would be interesting for you guys to see it. And if you're ever in need of an adjustable sawtooth generator, this is as simple as it gets. One thing you'll notice is this is a circuit that might look like it came out of Gerald's notebook. I'm using here a NPN transistor, but I'm not using the base of the transistor. I'm just using the collector and the emitter. And the reason for that is, as the voltage builds up in the circuit, it finally pushes itself through the collector and emitter here in kind of a burst. But in that burst, it's ramped up based upon this 0.1 microfarad capacitor here. So the bigger the capacitor, the slower the burst. The smaller the capacitor, the quicker the burst. And what that means is the output is going to either have these long ramping sawtooth waves or these really tall, pointy, quick dropping sawtooth waves. And so that's just basically how that circuit works. And I put it together with microwave transformer, some old potentiometer, all the stuff that came out of my junk bin from the thrift store. I'm putting in 32 volts because these things have ultra low current. But look, you can see here on the oscilloscope, perfect sawtooth waves. Now, if you look up how to make sawtooth waves, it's extremely complicated. You'd think it would be simple, but pretty much people think it takes an infinite number of sine waves and add it in a certain way to get this done. No, just Google Asaki oscillator, and with a few components, as you had seen, you can get these beautiful sawtooth waves for your needs. Now, this was my endeavor to improve the Slayer exciter circuit. As you know, Nathan has these very amazing Slayer circuits that he beats up all day and they keep on running. And so this overcomplicated Slayer exciter circuit, what I was trying to do is just protect the MOSFET. So these extra components, when you normally only need 3 components, is to try to protect the MOSFET, yet keep it a Slayer. The reason why I bring this up here is because it's one of my prototypes. It's close to working. But I also wanted to kind of show you how I diagram my circuits. Being dyslexic, I have to be extremely careful about color coding and drawing my schematics in a certain way. And if I don't draw the MOSFET just like it is physically, then I really have a hard time connecting it right. And so I just want to kind of show you how this is not really a schematic. This is really more of a dumbed down version for me because I'm dyslexic, but I thought it'd be worth sharing. It might help people who have similar kinds of struggles with concentration and looking at schematics. Just hand draw it and hand draw the components as they exist. The second thing I do is because of, try to flip it here, is I then take that and I actually write it on to a PCB board. And again, because of my dyslexia, I just pull out of the bin some resistors, capacitors, diodes, and I place them physically as I wrote it out in my homemade looking schematic and start connecting them. And so you can see that I'm starting to attach the components, and glue gun. The glue gun is the best tool for electronics hobbying. It allows you to secure things for the prototype, but allows you to pull them away real quickly. Also, you'll notice that I'll use these connectors. So I'm not doing a whole lot of soldering for things like the MOSFETs, the things that blow up. But I'll solder in the capacitors and usually the resistors because they're pretty durable. But just giving you some insight into some of my building practices. Here's a pretty picture of as it's getting completed. In fact, this is just about complete. And but you can see how it just follows the diagram that I wrote out. This was this was the prettiest wave form that I could get out of that circuit. So yeah, this is a huge failure. I don't even know what this is on the screen here. It looks like mountain peaks from some cover drawing of Lord of the Rings book or something, but it definitely doesn't look like a signal that shows it's working. So utter fail. But I wanted to go through you how I fail. I've always wished that when people are sharing how they do things, if they would just show their workbench and how they do things. I'm always pausing and expanding and trying to get, where do they put their screwdrivers? How do they work here and there? And so I'm going to be just sharing these, how I work, how my workbench looks like. And it's sort of an evolving thing. I kind of wanted to talk about this real quick. So this gray part here is a piece of metal that's it's a metal plate under my circuit board and under these black snake-looking things. And these black snake-looking things are clips, alligator clips, and they're magnetized to stick on any metal surface. And so I took this metal plate out of an old VCR, and I put it down and placed these magnetic alligator clips, and boom, I'm in production. I can move these because they're magnetic to different parts of this metal plate, and I can use them. And also, it's nice to have a metal plate when you're soldering. Solder tends to melt and burn everything but metal. And so I wanted to kind of point that out too, but it's just a preference that I have. I wish people talked about what's on their workbench and how they do things. So this is just a little example of that. Now I'm going to switch gears here to version 2 of making the mica capacitors. And I kind of want to show you how interesting the mica material is. First of all, if you remember in the last presentation, the highest capacitance value I was able to get out of all of this, or not all of this, but a third of this mica was about 3.9 nanofarads. And that was version 2. And so now I'm on version 3. I'm going to walk you through how I did that. And I'm going to get the capacitance up to 150 nanofarads. And so in effect, I will have built a high frequency, high power, high voltage capacitor to use in all my Tesla coils. And it will all be from things you can buy at the craft store or order on eBay, very inexpensive. And I'm looking forward to seeing the unique effects of a mica capacitor versus our standard plastic capacitors that we use. Oh, I put the torch on this so you could see immediately what it does to paper, or this is like a plastic paper, because I'm going to put a flame up to the mica. Now I'm putting a flame, a solid torch on a super, super thin piece of mica. And as you can see, there's no warping, there's no damage. Even glass would crack. And by the way, this is like 1/10 of a millimeter thick. And this just speaks to the amazing properties of mica and how it deals with temperature, how it can just take in all kinds of temperature and not even be phased. Now, that's why mica is used to be the output of microwave, the actual microwaves that go in to heat up your food. The microwaves will pass through the mica and warm up your food, and it has no effect on the mica. Let's see here. So I'm showing you the side view, how the mica is nice and straight. So in version 3 here, what I've done is, and excuse the Band-Aid there, is I'm taking a razor blade and I'm dividing the mica sheets that they sent me into more and more sheets of mica. In fact, in a 1/10 of a millimeter sheet of mica, I'm able to get sometimes up to 10 sheets, super thin. Yeah, they have all the properties of the mica. They're heat resistant. They're a great dielectric. And so what I began to do is just take 20 of these pieces of mica and slice them into as many wafers as I can. And as I'm doing this, I'm seeing more and more refraction of colors, more and more of those fractal color designs. So the mica gets really interesting when you start really slicing it thin by thin at what it does to light, which surprised me. One of the steps in building these microwave capacitors, and the reason why I'm getting in depth of these is I got some positive feedback on, hey, I want to be able to build mica capacitors like you for my projects. So I'm just doing a little bit of a drill down into my process. And so when it comes to high voltage, it's very important that you don't have any hand oils getting on your parts that you're going to be using to run high voltage electricity against, because the hand oil can become conductive. And so I'm using alcohol to wipe all of the mica and all of the aluminum before I put things together. And just to kind of give another example of that, if you use a PVC pipe for your Tesla coil, you have to sand off the ink. If you're going to really get into those really super high voltages, 1,000,000 volts, if you will, that ink on the PVC pipe, even though it's razor thin, it becomes conductive and can burn up your coil. So I'm just kind of following those same kind of precautions when I'm designing and building my high voltage components. Now, version 1 is on the left. I was able to get, on the right, I was able to get 352 picofarads per sheet of mica. On the left was my version 2. I'm able to get 890, that should say picofarads. That's wrong, typo, picofarads. So version 2, I was able to double or triple it almost. And now as we get into the version 3 here, I thought I'd point out, I throw the tape on the spool here. I'm left-handed, so my wife bought left-handed scissors for me. I know, small point, but these things help. We live in a right-handed world, so it's nice to have stuff like that. Now, in this picture here, I spoke about this a little bit last week. I'm just going to get a little bit more in depth here. One of the strips of copper goes on the underside of the wafers, and then another strip of copper goes on the top side of the wafers, and then they're folded in half, and then they're placed together. And this keeps one side of the plates away from the other side of the plate so the capacitor doesn't short out. And here I've bent it now, and you can kind of see how One of the leads is on the left, and that is going to have the same pattern on the left. On the right, it's going to have the other pattern, and this gives the 2 plates, but it also incorporates all of the underside plates on the right and all the overside plates on the left. And I found this. Now look, nobody's doing that I can find on the internet. No one's making capacitors like this, so I really had to knock my head against the desk to figure things out, and this seems like the best way. If you guys feel like there's a better way, please let me know. And before I move forward, I forgot to ask you guys, if you're in the chat and you want a comment or a question to be answered by me or Nathan or Ben or the crew, put a question mark in your comments. Just one question mark, doesn't matter where. And at the end, I'll be able to do perform a little hack and pull those out in a searchable format, and I can address them. And we can get all of you guys heard at the end of this. And so if you guys just put a question mark anywhere in your comments, doesn't matter. And we can pull those out by search and read them after this presentation. All right, so you see them, they're stacking up here. Now they're getting ready to go in the clamp. The clamp really helps the plates to get even closer together. There's 3 things that improve capacitance, and capacitance is just the storage ability to hold charge. One of them is the dielectric. So mica is a great dielectric, so that's what you want to think about in a capacitor to improve capacitance. The second is that you want to have the largest plate size, and so the aluminum that I tape to each side of the mica, the bigger those aluminum plates are, the increase in capacitance. And then third, how close you can get those plates together. The closer the plates, the higher the capacitance or the energy storage. And so when you saw me slicing the mica into thinner and thinner slices, that actually causes the capacitance to go up. It sounds counterintuitive. You would think more mica, more capacitance, more energy storage, but it's actually the opposite. The thinner you can slice the mica, the closer you can get the plates, the higher the energy storage. So I'm going to change gears here now. And here's where I wish we had the sound. Let me see. Nathan, is there a way we can get the sound on this? I'm sorry to throw this on you. But in this set of slides, I'm going to be teaching how to troubleshoot your ZVS, because the ZVS can be an unwieldy beast. But if you follow these couple of tricks that I do, you'll be able to keep your ZVS circuit running for as long as you want. Let's see. I'm not even hearing Nathan, so
just try to hit play and see if it does the sound. I don't know any way to fix it.
Okay. Let's see. Let's see. Did it? Here we go. All right. No worries. I'll tell you what's going on. Thank you, Nathan, for trying. Appreciate it. So what's happening here is when you have your ZVS connected to your variac, just as you begin to turn it, it's going to start making a real loud humming sound. And then turning this hand wheel on top, this knob up here at the top, it's going to give you resistance. It's going to start slowing you down. It's going to feel like your variac's full of molasses. The reason for that is too much current is being drawn from your variac. If you push past that resistance, if you allow that annoying noise that it makes to continue, then you're going to blow this fuse right here. You're just going to blow it. Not only that, you're going to destroy a whole bunch of more components on your ZVS board. So when you are adding power to your ZVS board on your variac and you just start to turn it and you hear that buzz and you hear feel the resistance, just stop. Don't fry it and find out. But do a couple things here that I'm going to share with you. Step one, there's 2 diodes on the input. So the variac comes from the bottom up through these diodes and then to the ZVS circuit. These diodes are notorious for shorting out. In fact, believe it or not, the hottest component on the ZVS are not the MOSFETs. It's these little guys here, these little turkeys. I have had so many headaches troubleshooting the ZVS board, only to miss the fact that on the input power from the Variac, it's these little culprits right here. So suspect your diodes, your input diodes first. And how you do that is you just put it on diode test on your meter. And one way it should show a voltage like 0.4 volts there. And the other way it should be an open circuit, so OL. And so there you go. So those are good working diodes. One way it should show a voltage 0.3, 0.4, 0.7 volts. Just depends on the type of diode. And connect it the other way, it should be open, should be OL, just like that. Most meters have that. Now, if it isn't, okay, so we're going to put those diodes back because they're good. And then we're going to go to the next culprit, the very next culprit. And you'll be surprised to find out it's not the MOSFETs, it's this diode. Now, it's kind of funny because you can see I put a plug, a green terminal connector here to plug and unplug that diode, because that diode is the next guy that'll get you upset and ruin your day. And so we'll remove that diode to test it. And as we tested the other input diodes, we're going to test this diode. This is a Schottky diode, but it works just like others. 0.3 volts one way, 0.32 there. The other way, it's an OL. There you go. The difference between Schottky diodes and regular diodes is Schottky diodes are really good at handling high frequency, and they can also handle a whole bunch of current. In fact, the Schottky that I had there can handle 500 amps of current. Yeah, 500 amps. It's pretty crazy, but that's the Schottky diode. All right, so the third culprit now are the MOSFETs. So I use these terminals because I can take out the MOSFET. Awesome. I can get my little transistor tester. It's this little blue oscope that I picked off on Amazon for like 40 bucks. Here I am trying to fit it in there, and I couldn't quite get it in there in this video. But let's see here. I might have these a little bit out of order. Let's see. Oh, I'm gonna try it again. Okay, sorry. Okay, so this is what I wanted to show you here. Let's see. So I was unable to show you the screen. When you place the transistor, the MOSFET in a transistor tester, and it's bad, it's going to show up as an inductor. An inductor is just a coil. Basically, it's showing up as a little coiled piece of copper wire. That means it's bad. That means it's not going to work. So that was the first MOSFET I tested, and that was bad. And now I'm going to test this one. Apologies for the bad angles. I'm learning how to record these things. Gonna lock it in there, press the button to test, and let's see what we get. There we go, MOSFET. Awesome. So that's what I do. Find the MOSFET, the culprit, and replace it. One thing I'll do is I use these aluminum, oh boy, heat sinks a lot. And yet, there we go. See that inductor. Okay, this is bad. Okay, so you're supposed to use a conductive grease when you attach the MOSFET to, let's see if I can pull it up here. Yeah, here we go. Instead of, so if you just screw the MOSFET to an aluminum heat sink, the heat sink won't work very well. It just won't. Your MOSFET will still die. What you need is either a conductive grease or these little silicone pads. And I have a little silicone pad. I know it's a little blurry here. I'm wondering if I can zoom in. No, I can't. So I get these little silicone pads. And the reason is that the conductive grease gets everywhere. And then once it gets everywhere, it lasts forever. I mean, in fact, if you stain your clothes with this conductive grease and your house is on fire, the only thing that will survive the fire is that little grease spot on your clothing. That's how tough this grease is. So I don't like it. It's weird because nobody mentions this in any of the videos I've seen on cooling down your components. But get these little pads and life is easy. So I have a bad MOSFET, so I'm going to my container that I got from Mauser, and I'm going to just unscrew the MOSFET from the heatsink. And yeah, that screwdriver doesn't work. I'm really good at these videos. But see that nice little pad? Love it. No grease. Now the conductive grease might be a little better in conducting, but not a whole lot better, not that I've noticed. So there you go. No mess, easy. And there you go. And I'm back up and running. Let's see here. And now I'm going to put the new MOSFET into the ZBS board. Gotta love these terminals. They're great. Swap in, swap out. All right. I bend them up because when I start moving some, like a light cool breeze across my workbench, they provide more cooling. I don't use any kind of fan cooling for my ZBS boards because they run efficiently. But if they're not running, now here I'm going back to the Variac, and instead of hearing that obnoxious buzzing sound and I'm fighting the resistance, it just moves smooth as butter. Next, I start seeing a waveform on the oscilloscope that looks promising, and look at that. My ZVS is happy as can be, all fixed. It was a bad MOSFET this time, and yeah, we're golden. So those are the big troubleshooting headaches of having a ZVS. So if you guys maybe want to bookmark these this little portion of the video, you can go back to it because taming of ZVS and troubleshooting it can be very overwhelming, and I hope this simplifies it. And of course, everybody needs their box of shame. So yeah, bad MOSFET, bye-bye. Now my box of shame used to be one of those dumpsters at construction sites. But now that I'm getting more used to the hobby, my box of shame is smaller and smaller. All right, so now we're going to change gears here to a new type of coil that I've been working on. So what I've found out is the cylinder shapes and the sphere shapes of the Death Star and my first version coils, they were relatively big. They gobbled up a lot of wire, and they were tough to epoxy. And so I thought, well, you know what? I'm going to have a next generation of these coils, and I'm going to deepen their grooves. And instead of 6 inches, they're going to be 3 inches. And yet you're going to be able to get the same power out of these little 3-inch coils as you would a conventional Tesla coil that's 3 feet tall, maybe 4 feet tall. And anybody wants to get into the numbers of that, I can tell you why. So I'm making these smaller coils, and this is just for ease of accessibility if you want to jump into the hobby, or ease for people who are already in the hobby and don't want 5-foot Tesla coils and all the hassle with that, but they want to have desktop plasma experiments. This is really next generation. And here I'm printing a whole bunch of new spheres and cylinders within this spirit of smaller and wider and deeper. If you remember, I made a polycarbonate sphere that was translucent, and it caught fire and smoked and it was horrible. I just found it wasn't a good insulator. It couldn't keep all the high volts in. It just spilled out. So this is PETG. This was recommended to me by good old Ian. And so it worked out first time on the first print. So I'm really pretty pleased with that. So hopefully, guys, I'll have this wound and up and running for the next Wednesday's presentation and show you guys what I've been wanting to do. Just cleaning up the PETG. It's really easy to clean up, a lot easier than I thought. So here now I'm designing several spheres out of different materials. So the left is PETG, the top white here is nylon, and then the bottom right here is the standard PLA. And I'm just going to be trying different materials to see if I can get different effects in my experiments. So now I'm going to change gears here again. In these series of slides and videos, I'm going to be experimenting, trying to emulate Nathan's, I don't know what to say, super exciting breakthroughs that he's made with his Tesla coils in the last week. And so what you're seeing here is my version of a Slayer exciter circuit. Instead of one resistor, I have two. I have one here, the blue here you can see. And then I have a potentiometer, a pot here, that's just a resistor that you can turn the knob and adjust the resistive value. And so this is a very tiny circuit. This coil here is not even 3 inches tall, and it's an inch wide. It only has a couple hundred turns of wire on it, a thin wire. So this is about as weak as a Slayer exciter coil that you can build. And I took out all of the fluorescent bulbs I had picked up at thrift stores, and I just threw it against, or put them on this little coil. And now I'm going to turn the knob. And there we go. Wow. This little coil powered quite a bit. I was really, really surprised at 24 volts. It's under an amp. It hangs out around at an amp. Now I'm going to crank up the voltage. And it's always important to know your current when you're testing, unless you want to just burn up your components and be resoldering all day. You can see, look at all the power. All of these fluorescent bulbs are being illuminated, and yet I'm getting a really nice discharge on the top. It's neat how Nathan has reintroduced the Slayer circuit, and there's just a lot of enthusiasm around the new types of experimentation with this really simple and cool circuit. And so I'm going to start, let's see here. I'm just going to play around here with lights again. Again, oddball fluorescent bulbs I found in my junk pile. Okay, so this is interesting. On the left is a patented, basically a CFL light bulb, and it's supposed to output a clinically tested frequency that instills a feeling, a good feeling of optimism, and it's supposed to help you come out of what is called a seasonal depression. And so that's the left light bulb. The right light bulb is what you pick up at Home Depot, and it's just a plain old CFL light bulb. The reason why I share this is because, of course, I'm an oddball and I have all kinds of miscellaneous stuff in my presentations. But also, too, it might be worth you going to a thrift store and finding one of these little health lamps, if you call them, because I used one, and what I call it, when this lights up here on the left, and you can't see it completely on this video, but I call the left light bulb here when I turn it on an eye massage. When I've been straining at soldering and straining, because I'm an old guy. When I turn on the left light bulb, it's like my eyes are tucked into bed, and they're given just this warm sensation. And I don't know if it's psychosomatic, but it works. And so I thought I'd share it with you guys, because these little tips I discover as I'm building these circuits. And so the company is called Verilux. And if you have questions about that at the end, I can share that with you and how to pick them up. again, here's the Slayer's exciter circuit, almost identical to Nathan's, except for the little potentiometer there. But here's where I'm going to start some experiments. But first, let's get close-ups of this display. There's an old washer. I got off an old bolt. There's the top load. And this aluminum I just sharpened. I'm not getting as close to the plasma discharge as I like with my phone camera, because the Slayer exciter definitely puts out a punch more than the ZBS, believe it or not. And so, yeah, but I thought I'd do kind of what I do with all my plasma videos, is give you different camera angles. Now, this is where I start to try to emulate Nathan in some of his newer experiments. You know how he puts the wire down the throat of the Tesla coil? Well, I 3D printed this little cone thing here to kind of make sure the wire goes down the middle. If the wire doesn't, it goes down the middle of the coil and it touches the sides, it'll start arcing and sparking inside, and then it'll cause damage. So I was trying to figure out how to alleviate that problem and not have my little coil set on fire. Oops, sorry, that was wrong button. So here we are. I'm going to start this first experiment. First thing I do is I try to get a breakout like Nathan does. All right, got a breakout, good. Following my wire into my own pile of dirt and sand. And then it comes out another wire, and look, wow, this was the first time I got this working. I am so excited. I mean, I was just full of glee when it worked for the first time, and just incredible. That fluorescent bulb's maybe 2 feet, maybe 18 inches, 2 feet. So it's not a dinky size, but it's not those big bulbs that Nathan has. But I also think Nathan has a bigger Slayer exciter Tesla coil. So I think everything here is proportional to Nathan's. Nathan has a good size Tesla coil. He has a good size lights, fluorescent bulbs, whereas I just have sort of a miniaturized version of his. Now here, I'm trying to see how far I can get. So this is 9 feet away, and yep, it goes in the dirt. And it's only touches the dirt. The wire doesn't connect to the other wire on the other side of the dirt. It's a real sandy dirt. It has a lot of water. Here you can see it's down the throat again. And I'm going to wait for a breakout. And then I'm going to go see, all right, I'm turning off one of the lights. And look at that. It's just, and this is without everything turned off. 9 feet away, super bright. So yeah, it's interesting. It's a 1-wire power, and it's going through the earth. Well, at least a little piece of earth that I put in between this light and the coil, that's Tesla coil. Here's I think I could kind of show you. Look, nothing special there, not connected to anything. So here, gonna get a breakout here again. Let's see. Not sure why it's not coming out. Oh, I didn't get a breakout in this one. Yeah, I just tuned this for the light. So you don't need a breakout. You can just slowly turn it to just get the light on. And I think this is the more efficient way. No breakout, just strictly the minimal power. Oh, we do have a breakout, but I think that happened later. But I can turn that breakout off and still have the light. So that was a great success, I think, a successful experiment. So here I'm putting the ring light here around it. I'm going into the dirt, coming out of the dirt. That was a better close up. And again, I'm powering that light bulb 9 feet away. Okay, so I'm showing you nothing's connected. Now this is a muddy sand that came out of my granddaughter's sandbox that they play in. It's real freezing cold up here in the frozen north, so I couldn't really get the shovel into the ground. It's frozen. But here I'm just experimenting after experimenting and finding things out. So now this is really interesting to me. If you go back to this, Let's see here. You saw me just put the light bulb into the mud. This wire is not connected. The other wire is not connected. But I did ground one side of this bulb. And so all you have is an ungrounded Slayer exciter Tesla coil, dinky one, and it goes down the throat and it goes into the mud here, and then it goes out the mud here. But this light here connected to earth ground, all of a sudden it just picks up the radiation from the mud here and lights things up. And so I thought that was fascinating. I know this is all very similar to what Nathan's doing, so I appreciate your patience. But it just is exciting for me to replicate his experiments. Not as much power going over here, but that's okay. It's 9 feet away. It's a bigger light bulb, so that makes sense. And you can see again, I've got a breakout, yeah. I think this is, oh yeah, this is another experiment. I think you guys might like this one. This one's interesting too. Oh, I'm getting a little enamored with the designs of the plasma. I know Nathan's are pretty fascinating designs as well. So here, this is what really fascinated me. I have this giant ring. I'm still putting the wires in the mud. And this ring it takes quite a bit to light this ring. And yet it's super bright from what's emanating from the mud. I mean, the power goes into the mud and it goes out of the mud over to that light 9 feet away, which is actually right here. Oh, it's still lighting too. But this ring is just placed on it on top. Yes, it has a little ground wire, but yet it's just picking up, I guess, electrons from the earth that can be excited. And this little piece of earth is pulling them out of the larger earth, the ground that's under my house, or vice versa. I'll leave that to Nathan and Gerald and Ben to comment on later. I think I'm doing something a little different here. Let's see, not connecting it to anything. Down the throat. Like I said, nobody puts it down the center of the coil. Super cool. Yeah, I just love. I love the plasma on this thin wire. Just takes all kinds of fascinating shapes. And look at these lights. These aren't even grounded. Okay, this is literally a loose wire. It's probably 18 inches away. This wire is not connected to anything. It's nowhere near the metal connections, and they're not grounded. So there's just a whole lot of something coming from these experiments. I can't wait to see what they come to in the coming weeks. And I do know Nathan and Gerald are working on some sort of really advancements in this. And so it's just fun to join them in this experimentation. Let's see if this is something different, or I'm just getting excited. Oh yeah, getting excited about the plasma again. Fun. I'm running between 24 and 32 volts. This smaller Slayer exciter Tesla coil setup, it just won't start oscillating less than 24 volts. And there it is. One of the ways I build circuit boards is it's a piece of copper here with fiberglass under it. I take my grinding wheel and I grind out lines, and then I just solder it to the lines. Yeah, it's not very high tech here, low tech, very low tech. Showing you the size of how dinky the coil is. It just fits in the palm of my hand. I don't even have power input. I just basically connect the power supply to an old capacitor from a stereo at the thrift store. So the setup's not really, I mean, it's just more about understanding the fundamental and playing with the fundamentals. And it's an intuition thing that I'm really trying to pick up on from Nathan and Gerald and Ben is is that, yeah, there's a lot of science behind this, and it's good to have a foundation in basic electronics, electrical theory. But when it comes down to it, there's this factor of really come close to the elements and building experiments like this that you just don't see on the internet. Almost done, guys. Thanks for hanging in there. I think that's a close-up. Oh, so this is my first layer exciter circuit. Look how cool that is. And believe it or not, it works. In fact, if I plug this little layer exciter circuit in, I can guarantee you that the MOSFET will die in 10 seconds. So yeah, this is a normal starting entry-level layer exciter. And it's funny, you see these all over the internet, these layer exciters, but they don't tell you you'll lose your MOSFET in a few seconds. You just have to burn a whole bunch of them until you figure it out. This is, again, like another generation. Just kind of sharing these because I went from the grinding of the copper plate to these copper rails. This helped simplify things in building these. Another construction technique. I ordered some rectangular wire. And so I'm going to be winding bifilers, trifilers, and this is a special kind of rectangular wire where it's 0.10 millimeters thick, but it's 1 millimeter wide. So it's an incredibly difficult thinness of wire to work with, but because it's 1 millimeter wide, it actually is nice to work with. So in effect, a small disc like this, you can get a couple thousand turns in your bifiler. And I think that'll not exemplify, but amplify the effects of normal bifilers who don't come close to thousands of turns. And so, you know me, I'm trying to build everything smaller yet more powerful. And this is one of the ones I'm pulling out of the work closet, and you can see how thin this is, but yet so I'm going to be starting that. So my much awaited 99.9% pure silver magnet wire arrived from China. It took 2 months, and it was tangled, and it's heartbreaking to see this tangled. Now this is 65,000 meters of 38 gauge pure silver magnet wire. I just spoke with the people in China who sent me this, and they said just cut off all the scraggly parts and we'll reimburse you. So I'm going to be wrapping coils with this. I thought I'd share that with you guys. That's coming down the pike. I ordered a kilo of bismuth. So I'm going to be building some bismuth capacitors. I've heard some talk about those. So I'm also going to be creating some bismuth rods to put in the center of my Tesla spheres and in the middle of my Tesla coils. So a lot of fun I'm planning on doing with bismuth. So let's see the next one. Now, this is an interesting tip I want to share with you guys. So I suffer from severe anxiety and depression on a clinical level. And I know I don't want to get too personal because I don't want to make anybody feel uncomfortable. But I know that a lot of people suffer from anxiety and depression. And
no medical.
Say again?
No medical.
Oh, okay. Well, I won't say anything medical then, but there is a computer sensor. Thank you for that, Nathan. There's a computer sensor that you hook on your ear. I'll show that here. There you go. Hook that onto your ear, and then the computer sensor on your ear will show you what's on the screen. And what's on the screen, you can interpret it, and that's all I can say. I will answer questions. Oh, so I'll put something. How can I do this? If you want me to email you information on this, I will.
Let's just drop it for now.
Yeah, thank you. Gotcha. We'll drop that. My messy lab. I always wish I could see people's labs. I wish people would always do a pan so I can see what they're working on, how they work. I learn a lot from that, and almost nobody does it. So I'm going to do it because I wish others would do it. No biggie if you don't want to do it. I don't want to give people pressure, but these posters here, my wife just had them made for me. These are tremendous. This is the wire gauge chart here. I use this wire gauge chart almost every day. This is Ohm's law, so this really helps me to just see it. And then when I'm looking at schematics, I don't know what half of them are. So I just take a peek here. Oh, that's a BJT, or that's a Schottky diode. And so quick reference, lots of fun. These are about 2 feet by 3 feet. And I just got them in. If you're interested, put it in the chat, and then we'll figure out how to get you the files for these because they're free. But I thought I'd share that. Let's see here. There's a close-up of them. We just had like Sam's Club print them in a larger size on cardboard. And yeah, here's a clearer picture of it. This is just really cool. I have a slow learning curve, and my dyslexia gets me confused all the time. So I usually will Google these different pieces of information. Now I don't have to. I can just sit in my chair and get quick answers. Let's see here. Not sure what that was for. Oh, there we go. The Verilux. So if you guys want to get a Verilux, this is what they look like. Thrift stores, they're like $3, $4. And I take the lights out of them. And or I'll just turn this one upside down and want to work in the lab. Again, it's just such a restful beam of light. I found a diode bank that emits the same frequencies. So this is very cool. I'll leave that at that. And this is the last slide, just to kind of give you an idea of what I'm working on directly. So if you recall, I was in the picofarads, and the highest mica capacitor I made was 3 nanofarads. Well, this is about a little over 1/10 of slicing the sheets of mica. And so according to my calculations, when I'm done, this is 14 nanofarads here. But when I get to 100 sheets of mica, this is going to be a 150 nanofarad capacitor. And that's going to be powering my next generation ZVS coil. And so this is what the next generation ZVS coil parts are going to look like. And huge credit to SciTube HD and Archangel, because they offer you the Gerber files to print this board on their channels. And so it's their amazing design. I'm going to just build my components, like my capacitors, and do my own take on it. So that's it. I want to thank you guys for being patient. My presentations are never short. I look forward to your comments and questions.
Right on. Thank you, Shawn. I appreciate it. Great job.
Thank you. That means
Yes,
a lot.
thank you. That was awesome.
Appreciate it. I hope you guys are learning something new each time.
Yes. Every time you present, we learn something fascinating. So what I learned is that you can produce like some really cool patterns with that spark gap that you have, or that.
Yeah.
So that was really unique. I want to touch on that for a moment, because you said that was like producing sacred geometry.
Yes.
Or it might have been.
You see it in the design, looking through the mica capacitors, how it was refracting the light, but that had that fractal sacred geometries inside. You could see them if you look it up the correct angles. If you have a super thin piece of wire like you saw, and Nathan does this all the time too, Yes, it seems to organize itself into different shapes.
Wow. And it's the shape dependent on the frequency, I'm assuming? Like
Thickness of
cymatics, maybe?
wire. It's more thickness of wire.
Or thickness of wire?
Yep, the input voltage. So if it's higher power, the length of how far it's sticking out. Like if you pull that way out, it'll start dancing for you. So a lot of
Right.
variables.
Yeah, because it's heavier or lighter. That makes sense.
Right. Cool.
But it's like plasma cymatics. I like it.
It is. Yeah, that's a good way to look at it. All right. We got an active chat here. So Nathan, anything stick out to you in the presentation?
I like the fact that you got that light bulb to lights from such a distance, and
cool.
the fact
was neat.
The fact that you use sand in your experiment instead of straight mud was awesome.
Oh, cool.
So, the silica in the sand is really what you want to understand there, because that's what's going to give you most capacitance. It's a mineral.
You know, that I was afraid that maybe it was going to fail. And then I was kind of nervous to tell you that, hey, I couldn't find dirt like yours. But when you smiled and said, no, that's better, I was like, oh, cool. Oh, and I'm on the right track.
Oh, yeah. Well, we have other experiments we'll show later that'll prove that turns out even better.
Very cool. Very cool. I'm trying to, what do you guys think about the capacitors?
The ones with the mica?
Yeah, the mica capacitors.
Number one, I never knew you can take a razor blade and cut those things down. That was awesome.
I didn't know that either. And then I didn't realize Micah could take such a beating too.
Yeah.
Yeah, that surprised me too. And it's funny because it's a really good dielectric, which just basically means it snaps back and forth real easy from high frequency. But it's also a really crazy insulator. So when I pulled that torch away on that super thin piece of mica, which you would expect to just melt, about 10 seconds, 15 seconds later, it was still super hot, incredibly hot. So I thought that was interesting too. Yeah, so I'm perusing the comments here, and here we have Speaker Shaker. Have you ever thought about making a Tesla coil in the shape of an hourglass, making it like a ventili tube? I think I'm saying that wrong, and a carburetor, or maybe even a pinch design so it does the plasma pinching thing. Maybe it would. Well, I did talk about the cylinder coil that I made, the updated one. And if you look at that, you can actually wind it into different designs. You can wind it as an hourglass. You can wind it as a cone. You can wind it as a diamond shape. And I'll be doing that in the coming weeks. And so, you're ahead of the game here, Speaker Shaker, or Spear Shaker, sorry. So Lexi used radio amplifiers to run through the Tesla coil. I'll let Nathan handle that one.
Radio amplifiers to run through the Tesla coil?
Yes, to run through the Tesla coil. Lexi.
I've never done it. I don't mess with the radio stuff that often, only to check and see where bubbles are in my garage when I create them. But no, never put it in there.
Okay. We got John Curley. When making a high voltage capacitor, you may need to have a significant dielectric board around the plates to keep from arcing over. Yeah, that's a really good point. My thinking is not using it for higher voltages than 1,000 volts. The reason for that is the capacitor, the output of the ZVS oscillator is only in the 600 to 800 volts range. it's not in the higher voltages that are on the other side of the primary coil or coil 1. It's coil 2 that you reach into those tens of thousands or hundreds of thousands of volts. And had the capacitors be on that side, yes, then the distance of the copper tape on the mica would come into play. So, but good point, something to think about. Okay, BT7274 says, what's going on here?
Yeah, we got it right after that. We told him.
Oh, cool. Interesting stuff. Ulysses, thank you. Let's see. I recall Nate got the flyer to lift. BT7274 is saying that?
Yeah, no, didn't lift that thing yet.
Okay. Oh, I see, Nathan. You're answering these. Sorry. Right. Beat Reachers says, enjoying trying to learn electronics. I'm an amateur, but think you are on it. Thank you. Let's see, David Gruel. I will be running my ZBS with 4 transistors in parallel for each side of the driver. Yeah, that's cool. I'm running a 4 MOSFET or 4 transistor ZVS as well. Though I have 2 transistors in series connected to 2 transistors in series. So it's 2 in parallel with 2. So a slightly change on that, but it'd be interesting to see how that goes. So if you could keep us up to date in the chat. Okay, we've got some really interesting comments here. I like my fluke. Yeah, I love my fluke. Let's see here. Let's see, you guys talking about the flyer. There's a big conversation about the flyer.
Yeah. Hey, Shawn, Teslas need a soft start. You want to address that real quick? Because your ZVS has a soft start.
Yeah, so the ZVS, if you just order it from Amazon and you hook it up and thinking that, oh, it says it needs 12 to 24 volts input, and if I just turn it on, I'm going to have it up and running and oscillating. And unfortunately, that's not true, because the ZVS, in order to get oscillating, it needs a quick inrush of voltage and current. And most power supplies don't provide that quick inrush of voltage and current. So the way to work around that is to put a switch between your power supply and the ZVS board. Leave that switch off, turn on your power supply, and once your power supply shows the right voltage and current, flip that switch. You'll have that quick inrush current to the ZVS. It'll start oscillating. And one of the ways you can tell it's oscillating is because it will be using less than an amp. If you just connect your ZVS to your 12-volt power supply, and you're noticing it's 6, 7, 10 amps, turn it off right away, because it's not oscillating, but it's definitely hurting things. And I know Nathan's nodding his head on that one.
Yeah, the wire's fried. Exactly what happens. Let me tell you, I've had more than one fires because of that. And it happens right in front of me, and I'm still doing it anyway. I know that sounds horrible, and I shouldn't, and Shawn would have shut it off right away. But I'm trying to complete the experiment before I explode it. So you got to push the limits on this stuff sometimes, and sometimes it's just that way.
I love when Nathan's talking calmly and he's moving methodically, and there's this thick billowing smoke coming off of one of his alligator clips. And when he sees it, he goes, oh, okay, well, this will end the presentation. He's all calm. I'm running for the fire extinguisher. It's just, yeah. It speaks to how used to smoke that he's gotten. That's what it speaks to.
I've blown up a lot of stuff, man. And these EVSs, man, they like to heat everything up. So if you're not in perfect oscillation, this thing is an absolute nightmare. And
Yes.
if you have it in perfect oscillation, a dollar store wire will run that thing.
Yeah. Yeah. David Gruel says if you run extra MOSFETs in parallel, it will reduce heat in your MOSFETs. Not really. Depends on what you're talking about. Definitely not in a Slayer circuit. I've tried it. I've literally soldered together MOSFETs in parallel to hopefully bring down the heat because it's given them more capacity. Nope. It'll fry 4 parallel soldered MOSFETs as quick as it'll fry 2 or fry 1. And I know that by experience. So it's great in theory. So I appreciate the comment. Unfortunately, it's just never panned out. Now, when it comes to hooking them in ZVS boards, the more MOSFETs than 2, 1 on each side, 1 turned off while the other's on, and vice versa to create oscillations. Adding more MOSFETs is a lot trickier, a lot more complex. So get more powerful 2 MOSFETs for your ZVS instead of adding MOSFETs is your best bet, unless you're a glutton for pain. Now, there is a dividend on adding more MOSFETs than 2, but you're going to have to face a lot more pain.
Okay, so I'm going to put this out there right here. 2SA1962, it's a PNP transistor. Run it in negative, not positive. That basically means that the power is pulling through your negative and not through your positive. I have a video on it. Best Slayer exciter circuit ever. It just takes that transistor and a 47 K ohm resistor, and you absolutely run 40 volts all day as long as you have a heat plate on there and a little fan that runs to it. You can run it all day. You can get a $5 one from Ryzen and just tap a hole in it and then hook your resistor to it. You're absolutely going to have amazing results. Like I said, 40 volts all day. You can run it at 20 volts all day and run any experiment you want. Absolutely the best Slayer exciter circuit you'll ever find. It's 2 parts, and you can count it as 3 parts if you count the heatsink. And the fan would be 4, apparently.
Thank you for re-emphasizing that, because simple's hard. I don't know why, but people trip over their own complexity and just zoom out and say it's 3 components. And as an experienced Slayer exciter builder, yeah, Slayer exciter circuits don't run like Nathan's. And you can go to the big guys, Electro Boom and these others, and they're not running their Slayers all day. They're turning them on real quick, showing you some fun stuff and turning them off. So it's getting them on all day to do the experiments that Nathan has made a great breakthrough in. So a lot of kind comments from Mike Does. He's actually saying, I'm a turkey, gobble gobble. Oh no, I shared a turkey. Sorry. Thanks, Mike. Don't. Oh, sorry, Mike Does. Let's see here. Nate, have you talked to the Tesla guys? Some out there are freaks.
I do talk to a couple Tesla guys, just like Shawn. We go to the same places and talk to people. They've all seemed pretty nice to me, and they've all gotten back to me, by the way. So, no, I haven't run into that kind of a trouble at all.
And like Nathan said, I share the sentiment. I reached out to them and they're super helpful. They want to help no matter how big the channel is. They really like people trying to emulate, or they want more people in the fold. They want more Tesla nerds like themselves. And so, yeah, I can double that, the good experience that Nathan's had. So David Gruel says, I'm working on a circuit that will self-resonate and adjust power needed according to power output readings and tune to the optimal frequency and voltage. it will step 20 volts up to 50 to 100,000 volts, or 50. Oh, I'm sorry, 50 times to 1,000 times the input. Very cool. Interesting. Stefang says, I like Shawn's subtle humor. Well, thank you. I'm a terrible joke teller. So thank you for that. Let's see, the sand is the key. Thank you, that Nathan. Yeah, I found that out. Appreciate it. Let's see, a Fat Finger McGee here. Not sure what that means. Mike says Tesla lit a bunch of light bulbs and it was wireless. If the voltage is high enough, it can find ground through the air. Yeah, I think Nathan's proven that, or showing that, right? What do you think, Nathan?
Well, there's a misconception about a Tesla coil in the distance that it goes. If you're running it in DC, the distance is compromised by the breakout. So every time you get breakout, it reduces the distance. So because it's allowing heat out of the system, so the heat cannot transfer through the Tesla coil itself to push out the field. One way to minimize that is to cap the bottom and top of your number 2 coil, which will then put out the radiant field further because you're capturing the heat, and the heat stays in the system more so you can push it out further. When you get to a really big Tesla coil, all the rules completely change. But anything under 80 volts, it's pretty much that way.
Yeah, thank you for that. Yeah, good answer. It's sort of opposite of how people look at them, and it's an important distinction. All right, nice words.
Yeah, most Tesla coils that you see on the internet, except for very few, are low power, and they'll hit 5 feet and can't break 5 feet. That's one of the key rules of a Tesla coil. You have to understand heat and cooling in order to push more than 5 feet.
And yeah, that's been used a lot in your descriptions lately, is the focus on cold and heat. And you referred to them as understanding the flow.
Yes.
Do you want to maybe dig into that, or?
So the outside radiant energy is heat. It takes your amps, converts it to heat and radiant energy, right? If I want to increase that, I hook it to ground. The ground itself is going to pump more heat in there, so it's going to push more amps. What you have to understand is you still have an air core transformer. You're still transforming amps to volts. And if you don't think that you are, just look at the way a regular transformer works. When you step it up or step it down, you're changing your amps and trading for volts, or you're trading your volts for amps. We know that there's a correlation there. Now, the key factor in this is that you can add to the amps by adding heat. You're adding to the circuit. So when you put it into the ground, you get 20% more because you're adding heat to the circuit, which adds amps to the circuit, which pushes the field further. Now, that also comes into play when you cap your Tesla coil on the top and bottom on the number 2. That allows you to push more heat, which is more amps through the circuit, and push the field out more. That means that the opposite is also true. If you open the top and bottom up, you have less heat in there. It doesn't move as far unless you change the structure on the inside. As you put a rod down your Tesla coil, it will now produce more amps in there because it's forcing it away from the center and pushing it to the outside, but it'll also create a draw with that rod down the Tesla coil, which will pull cold or at room temperature. So what happens now is now you can manipulate the temperature in your Tesla coil based on whatever you connect that wire to. So there's a big understanding between hot and cold. Now, as it's a cold circuit, when it comes out of the top of the Tesla coil right down the center, when you connect it to something, if you double ground, so you had a ground in your original number 2 coil, now you're going to create a ground in another area after, like a light bulb or something. Now that light bulb's going to light up even brighter because it's now pulling the amps from the ground on that second ground and giving amps to your volts that are coming out through the center. You are technically adding volts and amps together, whether you know it or not, and you're getting a higher wattage. So that's one way to do it. So you have to understand heat in your system and cold in your system and how to manipulate it. If you can get an air core transformer of any kind and reduce the heat below ambient temperature, below the temperature in the room, it will last a lot longer after the circuit goes off until it reaches the temperature of the room again. It's so important. Yeah, it's so important to learn hot and cold systems. And when I say cold, you're just going for room temperature and under 10 degrees, any lower than that, and you're getting into superconductor levels. So at room temperature, this is the whole important part of this. We're going to build a room temperature superconductor soon, and this is how you're going to do it through that cold side of the circuit.
And that's a really good explanation. Are hot and cold still measured in degrees Fahrenheit or Celsius, or is there a new unit for this flow of hot and cold?
No, you measure them the same way. Just take your basic meter from Home Depot and make sure it drops 10 degrees. And if it does, this thing is going to be a brilliant circuit for you. If you are getting heat in your system in there without the second ground, then you're doing something wrong. You got something wrong. You got something connected somewhere. You got something touching the side of the walls of your Tesla coil. Something else is going on, and you'll have to correct that.
It's an important distinction. I have a infrared camera. It has a sort of large screen. It's real time. And I use heat as an indicator of how my circuit's performing. Anything new, I look through the viewer and see where the heat is, and it tells me how the circuit is working. So I know this is different than what you're saying, but heat does become important when understanding how your circuits are doing. And it seems like you're taking it kind of to another level of saying the flow and the temperatures need to be within certain ranges in order to tell the health of your circuit. And I think that's what's the new thing. And I know Genetic Jabber here says, I'm sorry, Nathan, but it's adding capacitance, not heat or cold. What do you think about that comment?
No. Look, I know it's adding capacitance when you add something to the wire down the Tesla coil, okay? Yes, it adds capacitance there. But there's a hot and cold factor. That's why 99% of the people can't do what I do. They fail because they don't understand hot and cold. And if it's just hot energy, what's the point? I might as well just take a huge rod and shove it down my Tesla coil that's the size of the inside and call it a day, right? But the thing is, it'll blow up your Tesla coil and every circuit you have connected to it. And it lights fires. So it is about hot and cold. And most people haven't pulled a cold circuit, so they wouldn't understand. I did a circuit a little while back where I put it out today. It has a ring light. And I just hooked it to a piece of aluminum. It's a cold circuit. All it is connected to the center rod of my Tesla coil, put down, goes to the ring, and then the light sits on top of it. This is how you know you have a cold circuit. I touch the light, right? Heat goes to the light because I'm hot. Now, what happens to me? The energy is pulled out of me, so my heat level drops. Okay?
You get cold? You actually get cold or feel chilled?
Yes, you do. I had chills I had them for about 3 hours afterward. This thing, it's pulling it. So when you put it to ground, it's pulling the heat out of the ground. The heat's converted to amps. So it absolutely works on the cold side. And everybody who's ever made a cold circuit the right way knows that.
Very, very good points. Thanks for explaining that or expounding on that. I just wanted to pick a couple more things from the comments, if that's okay. And then I know Ben has some updates on his experiments, which I'm very excited to see. So does this sound good for you, Ben? Just a couple more comments and we'll jump into your video.
Sounds good.
Awesome, sir. Let's see. Genetic Jabber says, when you're adding capacitance, the operating frequency will go up, and this translates to heat faster switching. I think that's directed toward you again, Nathan, that comment.
The operating frequency goes down when you add. Here's the thing. You're in capacitance at the beginning of the circuit. It's, I think, where he's at, Shawn.
Mm-hmm.
That would be more on your side. On
Yeah.
my side, when the wire goes down the Tesla coil, it doesn't work that way. It adds, I want to say this, it'll lower your frequency as it adds capacitance. So on the cold side of it, when you pull it out of there, that's what it'll do. And you'll pull it right out of the range on your Tesla coil unless you can find a wall to wall it off.
Yeah, and I think I think we're all in alignment on this one, because when I was adding lights to the Slayer exciter circuit, I actually had my oscope measuring the frequency. And as I was adding light, or when I put the wire in the mud, as I was adding things, the resonant frequency was dropping. It was this level, and it got lower and lower and lower because they were all capacitors. Yeah, a piece of mud's not a capacitor technically. A fluorescent bulb is not a capacitor technically, but they add capacitance to the circuit, driving down the frequency. And so I'm not sure if I shared that in the presentation, but that was noticeable in my experiments.
Mm-hmm.
All right, we'll take one more comment here. Let's see here. Boy, lots of good stuff here. I'll just take this one. Nathan, do an experiment with two of the same circuits. Make one hot and one cold, and show it under infrared.
When I get an infrared camera, absolutely.
Yeah, they're not cheap. They are not cheap. I have a lower end one, and it was yeah, they're not cheap. A decent one's not cheap, I should say. All right. Well, thank you guys for the comments. I'll be going through them again, and we'll have some more interaction after Ben's video.
All right, Ben.
Yes.
All right. So if you guys been following my research, I recently realized that I was not measuring the current correctly. And again, this is a learning process for me. I'm still learning this. I've only been testing these coils for about a year now. And I've learned more in the last month than I have in that entire, rest of that year. So with that said, we did find some old videos of Daniel Nunes where he's talking about and going through his setup. So I believe I have the correct measurements now. I just wanted to rectify something that I said the other day on the stream regarding the output and input data. Michael Morel brought it to my attention that I was not factoring in the duty cycle for that. So that significantly reduces our output wattage. So I know we showed like 18.5 or 18.9 watts on the output, but adjusted for the duty cycle, which was 90 off, 10 on, that's only about 1.5 watts output. And that's why we're not seeing that energy actually translated, even though it was exciting that 120 volt neon, yellow neon, with only 5.5 volts. So that was pretty incredible in its own right, but we weren't seeing the gains that we were expecting. So going over some of the old footage, it was noted to me by what Daniel said that he never actually got energy gains from the Joule Thief. So he only got energy gains from the stereo output using a true AC sine wave. So now we have since pivoted back to the stereo board. So let's move back to the stereo board. So as I was saying, Daniel said the only time he got extra energy gains was with a true AC sine wave. Now this makes sense with our torsion theory. By effectively adding energy in both directions of the coil, you are creating two counter-rotating fields that create a 0 point on the coil's equatorial plane or neutral plane between the two electromagnetic fields. We know that the two fields of study that have shown promising evidence for OU are torsion physics and plasma physics. So what does this have to do with our waveform? By limiting our waveform to one direction in the coil, you can get interesting effects, but not, as I've observed, no OU, no over unity or extra gains. Even by introducing the pulse in both directions of the coil simply does not produce the necessary requirements, in my opinion, for OU at this time. There might be some modifications we can do to the circuit, specifically capturing some of that wasted EMF and using pickup coils. But at this time, we are going back to the stereo board because it's going to be the easiest, in my opinion. So it is my belief that you have to have the AC sine wave to have the smooth transition between the back and forth movement inside the coil in both directions. It is also my belief that by having a 1-to-2 ratio of coil diameter instead of the 1-to-5 significantly reduces the coil's ability to squeeze the field on top of each other to produce that 0 point. Now, this means the inner diameter we have on the coil that we're testing is 3 inches and the outer diameter is 6 inches. This is a 1-to-2 ratio. We want to aim for a tighter inner diameter. So we want to compress that field a little bit more and have those wires a little bit closer to each other in the center. And that's just a theory I have. So the next coil we print out is going to be the 1-to-5, which is what we found are the specs for the PoE coil that Daniel Nunez was selling on his website at one point. Not that you can't get close in these other coils, but it seems that having a tighter inner diameter might be what is required for practical applications of this coil for real energy gains. If this setup pans out, it couldn't have come with a better time because winter's coming up, and the most expensive thing to run in my single bedroom apartment is the inefficient and ancient HVAC unit for my apartment. So the good thing is, though, once we crack this efficiency issue, I know exactly how Daniel Nunez used the coil for efficient induction heating. So with that, I'm going to pull up a couple of diagrams to show you the circuit that I'm working with before I play the video.
Sounds good.
Yeah.
Awesome. So let's go to the data sheet here. I can make this public if you guys want. You want me to share this? It's got some information. I just jotted it down for the presentation today, but it's got a couple of links and stuff. So here is the diagram that I'm using now, currently with the stereo amp receiver and the tone generator. So we have two versions of this circuit. One is a closed circuit, and the other one is an open circuit. Now, the closed circuit doesn't have a load on it, but it closes it connects the end of channel A to the beginning of channel B. Now, this is supposed to be the way that you use it for a stereo speaker or home theater or something like that. And the open circuit is the way you're supposed to use it for practical applications in lighting and using specifically fluorescent tubes, 10 to 40 watts they have here for the load. Now I'm using, and I only got this to kind of work by using a hybrid method where I'm actually closing, I'm using the open circuit here with the capacitor, 0.15 unifarad capacitor, 2000 HV Tesla cap, by the way. So I have the start of A connected to the end of B. So I have those two connected as well. And I believe this is because the inner to outer diameter issue, it needs that extra length and wire maybe to create more strength in the field. I don't know. Just a theory I have at this time. I could be completely off on that. But this method that I'm using right now, Michael Morell got like a very decent amount of ozone with only 43 watts, which is incredible. Even Daniel Nunez claimed he only got it at 93 watts. So already we're experiencing maybe a more efficient system if we know how to crack it, maybe. So that was really cool, but he did have to clear out his, apartment because it was just filled with ozone, and it's very dangerous to do that. So this is be safe. Don't do this if you don't have a well ventilated area, and we're not liable for any harm or damages that you incur. But that's how I have it set up, and I'm going to show you the video of my results. We finally have the current measured correctly, and the voltage is being measured pretty as accurately as we can get it on the O-scope. The O-scope I have is pretty cheap, so it doesn't actually show the numbers on the side or anything. It has the grid, but we can gauge it with the grid of approximately the efficiency of the system. So until we increase our upgrade our equipment, we won't have an exact idea of the efficiency. So keep that in mind.
Sounds good.
All right. With that, I'm going to open this video. Give me 1 second. Okay. All right. Can you guys see that?
Mm-hmm.
Yes.
I'm gonna blow it up.
Sounds good.
Might be more accurate current reading. We have 0.45 amps going into the stereo amp. I just measured it. I'll measure it again in a second, but we have 3 0.05 milliamps coming out. So a significant loss in the amperage. I'm not sure if that makes sense, but the current is being read correctly because the settings are correct now. Before I couldn't get a reading except on DC, and I was like, well, this might not be accurate if it's on DC and not AC. Now we are picking up the correct frequency. We are also picking up a number under the AC setting here. So we're at 3.30 milliamps on the output, directly connected in series before the load. So you got the negative connected to the line off the cap, and then you got the positive connected. I'm sorry, you got the negative connected to the load, and then the positive connected to the cap. So this is the output, and we're going to switch it. Okay. Okay. Now, obviously, having the multimeter hooked up is going to change the impedance of the system, and it's just amperage. So we have 0.24 amps going into the stereo amp now, and coming out. This was a mistake, and I'll correct it. I literally learned the last piece of this as I'm filming. So I'm not sure I get this. This is because the load isn't connected. I don't really understand what's going on here. These numbers do seem to be consistent. We're going to be testing more coils to compare and contrast numbers. But, I mean, let's see. We'll hook up the probe, or we'll switch the probe just in case. I had it backwards. We get the same. All right, and we're going to go monitor the current now. Let's see. So this is, or we're going to monitor the voltage. All right, so this is the voltage out. It's a probe connected directly to the power rail. We're at 20 volts resolution, so we're just at the 10 volt line, the middle line there, maybe slightly above it in some peaks. So we're just at the 10 volt line there. Let's change this. We don't have the load hooked up right now at the moment. So we're going to put this right on the cap. All right, so we're reading right off the cap. And again, that's almost exactly 10 volts, right? AC. So let's read the input now, or the output of the stereo amp. We'll put that probe right there. Let's adjust the probe. Yeah, look at that. It's either exactly the same voltage. It's either exactly the same voltage or slightly less. The duty cycle did not skip a beat.
Nice.
So I think these are some significant results right here. See, in a minute, I hook up the load and get the correct current. 0.90. I didn't realize you couldn't measure the current correctly without the load. Out of the stereo amp, as confirmed, hopefully confirmed with this AC setting, which I could not get to read before. But as you see, it tells you which plugs to plug it in when you switch. They're in the right place for this reading. And then we switch it to AC. Now let's move this one more time over. So the correct output for the milliamps is 3.6 milliamps. And you'll see that in a second. So it's not 90. When I turn on the load. So what we're going to do is connect this right to the load. In between the load and the cap. Then we connect the power back. Oh. All right. And look at that. 3.3 milliamps. And it's registering the correct frequency and everything. Exactly the correct frequency. Actually, that's 12.55, not 12.54. So almost exactly. Pretty close. Again, we have the multimeter positive hooked right up to the positive of the rail, and the negative hooked right up to where that goes into the rail. So it's in series between the load and the capacitor here on the side. That's a 2000 volt HV, 2000 HV Tesla cap, 0.15 unifarad. And you notice this is on. This is not connected to anything. That's just connected to the coil. That's not hooked up at all, just to the LED. That's picking up wireless energy here, so we know we're in resonance. That's our indicator light for resonance, or a resonance area. Maybe not the resonance zone that we need for OU specifically, but it is a zone that is producing resonance within the circuit here. And we all know that there are harmonics of those resonance areas. So I have a theory that different ranges produce different effects. And as you can see, this is the output again. Nope, I'm sorry. This is the input. So this is the input. See, that's the input before it hits the coil.
Is your probe broken?
Yeah, it's a little cheap. I think it got a little broken, so I gotta kind of like push it in a little bit. Before it hits the coil, that's the input. I'm gonna take that one more time and put that directly on the load output. This is the point where I realized I can't measure. I need to measure the voltage without the load and the current with the load. And there's like, it's a 2-part video where I'm literally putting this last piece together, like as I'm filming this. So give me 1 second and I'll load the second part of that.
Now you got to open up that meter, Ben, and see what's loose.
Yeah. Yeah, I know exactly. It's just a cheap meter. You know, I got to tighten something. That's all.
Cheap or not, it's part of your tools you use. So,
Well,
see if
I
it
need
just needs to be
proper-
soldered.
Yeah, I need to get a proper oscilloscope, like a nice one. So let me load the next one.
Yeah, Ben, let me know. There's the cheapest, highest quality oscope is what I have actually, and it's not like super cheap, but it runs about $300. So let me know and I can get you the info.
Yeah, sure. I'll email you.
Awesome.
All right. Can you guys see this?
Mm-hmm.
Okay, this is the second part. Sorry about that. I had to unplug the load because obviously the load's taking some voltage and it's dividing it, so it's not going to give us an accurate reading of exactly how much is coming out of this capacitor. I think that's why the wave was running low. So I disconnected the load, and now, as you can see, it's got its full potential. It's right up against the middle line, which is the 10-volt line. And we'll change this. Take that right off the cap. Put that right on the input again, just to compare one more time. Yeah, it's slightly more voltage on the output.
Wow.
And you can read the current. Oh, the current won't read because the load's not hooked up. That's why it wouldn't read. Okay, that makes sense. There's not enough of a load in this to actually read it, maybe. Too much impedance or something, I don't know. So we hook the load back up. Oh, it's actually not completing the circuit. See, I'm learning, but I got it.
Nice.
Yeah.
3.30.
We're all learning.
Yeah, and then you'll see one more time. I'll hook it up again and get the right reading for the current on the output of the stereo amp. All right. Oh, there we go. There's the more accurate reading.
Nice.
Okay, so we have 3.6 instead of 3.3 milliamps. That makes more sense. I was like, why is it reading 0.90 milliamps? Because the load wasn't connected. So you disconnect the load, and it goes back to 90. Okay, that makes sense. So the thing that I don't get is why isn't this reading while no load is connected on the output? That's a big question right now. We want to make sure that we're seeing all the right numbers and we're not misreading this. Hook the load back up. 3.6, 3.7 milliamps going in. And we just toward that for a second. Right in between. All right. Let me plug this in. Power. Oh. All right. That's that. So it's very dangerous what I'm doing, not disconnect or not turning off the system, but I wanted to be sure that I didn't like accidentally misadjust something while turning it back on or whatever. I wanted to, have it directly translate. So that's the only reason I do not recommend you doing it that way. I will not be doing it that way again. The output, that's what the load's getting, 3.3 milliamps. So it's basically maintaining the current while slightly increasing the voltage. And that is, I hate these cameras, man. Zoom in and clear up. There you go. So focus. There's AC right there, registering the correct frequency now. And it seems like everything is, I think it seems like all our boxes are checked regarding making sure we're reading the current right. Okay. So there'll be further testing needed to verify or refute this. There is always a chance that I'm still doing this wrong, but we do know it's possible to get over unity with these coils. We do know that when you get over unity, you hear that hum like you hear now. Watch, disconnect. Hear that? Kind of hear it.
It's hard on the with the camera.
And then we also know that when they're working correctly, we do see a slight loss of current on the output side, specifically because Michael and I think that it's using a little bit of that current to sustain the voltage amplification. Now, this is just a theory. We don't know exactly what's going on, but it's doing everything that Daniel Nunes said it would do when it's working correctly, including the resonance proven by the wireless induction here. All right. And that concludes my update on the new system for phase 2, which we might be going back to be using the stereo amp board, along with maybe some pulsed circuit for a motor. So right now it looks good, but we need our team to verify this, and we need our team to look at these numbers and look at this video and make sure everything is kosher before I officially release anything. I don't want to jump the gun again.
That's cool, Ben.
Yeah.
Yeah.
I mean, when you talk about you're getting the same indications as the Nuneses, sorry.
Nunez. Yeah, I always mispronounce it. I'm sorry too.
No, it's husband and wife. If I remember correctly,
yes.
Their team. So if you're getting the same indications that follow their indications or indicators, then are you feeling like the same inputs and outputs are the same and you're eking out the same efficiencies, or because if you could summarize, because I was following your experiment, but I was getting a little lost in the details.
So it looks like we're getting the same sort of efficiency, and that's kind of what I was going to lead into, honestly. It's my bad. The video isn't really organized well. I wasn't intending to release it, but I really wanted Nathan to take a look at it, and you, Shawn, to make sure I was doing everything correctly. I feel confident that it is the right way to measure it now, just because of everything I've seen in the past week regarding more of Nunez's work. But going back to your question, so what this specifically means is we're seeing around the same level of efficiency if the numbers are accurate, assuming they're accurate. We're seeing the same level of efficiency around 100% or 100.1 or 0.2% efficiency, and that aligns with this paper that I have. And I'll post this in chat in a minute. Actually, I'll post it in chat right now. So this is the paper that was released, and let me actually bring it up.
Is that the research paper I sent you?
I think that might have been the one you sent me. Yes.
With the 100 or 101%?
Yes, with the efficiency or optimization of energy using vortex coil technology. So what I'd like to read here, I'd like to read a little tidbit here, their conclusion, and it's very interesting. From observations, we see that an increase in voltage causes the current to increase according to Ohm's law, which states that voltage is directly proportional to current. The formula is as shown in equation 1, and they have all the math breakdown for this. The calculations above show the average input and output voltage. From observations, the output voltage is slightly higher than the input voltage. To calculate efficiency, we use the formula, and then they have the formula here. And it says, our calculations show that the coil is highly efficient, proving the theory proposed earlier about the Rodin coil. All right. And it says, from table 2, we discovered that an increase in the cable around the coil increases the electromagnetic voltage at the center of the coil. As the line is increased, the voltage increases. This is because the electromagnetic flux emanates from the center, and the number of coils increases the voltage. In this current relationship, we found out that it obeys Ohm's law without any losses due to the load connected to it. It acts like a pure conductor without resistance, making the voltage proportional to the current. During testing, an electromagnetic field originated at the center of the coil, generating energy. So, and they say after testing the coil, it was discovered that they had no loss in voltage or current and just a slight rise in output, about 0.1, giving the impression of 100% efficiency. Despite this positive outcome, its expectations are not fully realized. So they're getting really, really a COP of at least 1, right? You know, we can say that 0.1 is maybe some error threshold or a correction factor, right? So, and it's obeying Ohm's law for them, but it is not doing what Daniel Nunes and others have replicated with the Nunes open circuit method. And I don't think they're using the open circuit method. It looks like they're using the pickup method. So they're using pickup coils around that are wrapped around the coil.
So what do you mean pickup coils? Not the individual pickup coils like Nathan. They're actually wrapped around the main coil?
Yes, they're embedded into the coil. See, can you see? Yeah, so it's let me zoom in a little bit. It's hard to see. Oh,
yeah, it is hard to see.
This I zoomed in and the ad zoomed in. Where is it? Okay, so can you see that a little better?
Yes.
So do you see these strips that are kind of like yeah, they're vertical.
Yeah,
so I was just gonna say those are the pickups that they're using. And pickups are a good option, but in order to get OU or extra energy gains, you really have to be utilizing that open circuit method according to Daniel Nunes. So going back to this right here, this method on the right.
Gotcha.
Yep, the load and the capacitor are key. You know, the capacitance and the load, because it's all resonating in the same circuit. You know, it's all using the same resonance. That's why the circuit hums.
Yeah, gotcha.
It literally sings to you when you're in resonance, and it's almost like a cool moment where you're like, wow, this is doing something really unique. You know,
normally when your circuit's noisy, it's a bad thing. So that's a real fascinating result.
Yes, it's an indicator when you're in resonance. Like if your coil's not humming or singing, you're not in the right frequency. And that's what we've noticed, and that's what Daniel Nunes specifically walked somebody through on one of their live streams, and he's like talking about it. Yeah, it's very fascinating, but it's just an indicator along with. He didn't talk about this, but Michael and I kind of devised this method of using the wireless induction as an indicator as well. So if you have two coils that you're testing with, leave one on top of one, you know, that's not connected. Just put in a little LED connected to, you know, the start and finish of one of the outputs channels. And then that's all you have to do is just leave it there. And then you can go sweep through the frequencies and kind of find that sweet spot by looking at the light up.
So yeah, using LEDs as indicators helped me so much with my ZVSs. You say wireless induction. Are you saying that LED is not connected to anything?
Nope. It's just sitting on top of the Rodin coil, and I can pick it up. Or actually, it's sitting underneath it. I'm using the bottom one as the pickup. Sorry. The Mark 1 was the one I was connected to, and the Christmas coil wasn't connected to anything but the LEDs. But if it was the other way around, I could pick that up, you know, and it would still light up quite a bit off the top, like a normal Tesla coil.
That's amazing. Yeah, that's awesome. talks about that radiant energy that's coming from the vortex coil or the rodent. Wow.
Exactly. And another indicator is that, that pinkish glow that you get in the red neons. If you're getting that pinkish glow, that means, you're within some kind of good range, some kind of golden zone there.
You're talking about the wireless induction connection for the
No,
neon?
so I'm talking about like when you have the jewel thief connected. So do I have it on here? Oh, I don't have it. Let me.
No, that's cool. I just was wondering how, if the neon's in the circuit, then you're
Oh,
going
here
to
it
have to get some higher voltages.
Right. Yeah. So no, the jewel. Well, yes, exactly. And we want to put more power into the system, and I think power is a factor as well. We need like a 200-watt guitar amp instead of like the mini board that I have, just to see what this is capable of. Because I was gonna play another video, if you don't mind, Nathan, if it's not.
Yeah, go for it.
Yeah.
It's a video by Justine, and he it's an older video, but he replicated Daniel Nunez's work, and he walks you through exactly what he did, and he's talking about everything in detail, and it's very relevant. And I think it's important that people see this video because he does a brilliant job of kind of explaining it.
There's no music in there, right?
No music, absolutely.
Okay, good.
Yeah. So give me 1 second.
That's interesting how when you get it to hum, it starts on that light. Is that what you said?
Yeah. Yep. Isn't that cool?
That's awesome.
Yeah. Awesome.
And no lights when it's not humming, huh?
Nope.
It's too good
No
indicator.
joy.
And you know what's also weird? And I think this has to do with my inner to outer diameter ratio again. It has a wide range where that wireless happens, and you can you can hear the hum still slightly in certain areas, but in certain areas you can hear it like going up and down in volume, the hum, and the you can see the light bulb, like it's still kind of on, and it doesn't really diminish. It's really interesting. Like you don't really see a reduction; it just goes on and off.
Gotcha.
It's really weird. But yeah, let me put up this last one.
It's been a long time since I have made a video now. Various reasons for that, but a lot of things have been done in one way, in another way not too much. I have remade many of the coils and bought some stuff like an amplifier that I've been told it's been good for this stuff, and an oscilloscope. I don't remember if I had that last time I made a video, but and also have tried with making this one, which is
How
pretty much
smaller his
exactly
inner
the way
diameter
Daniel
is?
makes his, just to see
Hmm.
if that works and how that works. And I have made a smaller version, and this one, which I showed last, I think, added just more wires, and a smaller version of that one.
That
They
one
all
looks a little closer. I
work
don't
in
know. It's
different
hard to
way,
tell.
though. What I noticed with this exact or not exact, but this version of making it, you can only then connect it in one way for it to work. While if you these or the way he did it previously, you have more options. This is the amplifier that many others also use. And now I'm pretty much just going to show that yes, you have over unity, though not too much, or the coil is not running optimally because of this is an audio amplifier that only works at approximately or efficiently at below 20 kilohertz. It works a little bit above, but not too much. So if you go too high, it's very little efficient. So this coil actually works most efficiently at 39 kilohertz, but that's too high. So I'm just running in it, as you can see, 27. But you still get some, and as you can see here, blue is out from the coil and yellow is into the coil. I'm just measuring directly in and out of the coil now. And here is two identical measurements. That is measuring the current, measuring the signal current here into the coil, and this one is measuring the DC output because I'm running it through two rectifier diodes here, this capacitor. So it's a DC current and an AC current in, DC current out. And the
They're getting
DC
a slight
voltage directly over the LEDs here is measured 98 volts. So we have, as you might be able to see here, 70 volts signal in with 13 milliamps, and 98 volts and 18 milliamps DC running through the LEDs here. So it makes it about, if you compare the AC measurement in and the DC out, you get approximately twice the effect in wattage. So yes, you have, but I'm still working on a way to make it without running it through an audio amplifier, make my own circuits. I made my own oscillator circuit here with a variable frequency. But I'm still working on the amplifier circuit, which is only like this at the moment, very simplistic, but still it does the job of amplifying the signal, but it doesn't trigger the coil, kind of. So I need to stabilize it and some stuff work with it. I'm not sure yet, but that's something I'm still working on. I'm not going to show the schematics for the oscillator here because...
So I think this video does a good job of kind of explaining some of the missing details about these coils here. Specifically that he said that utilizing that one coil versus the other, you only have one option to hook it up right, whether versus the other coil, you have many options, right? So depending on the type of wind and pattern and size of the coil, I'm assuming the inner to outer diameter, there's different applications for it, and you probably have different limitations too.
Yes.
So that's where I am right now. That's all the updates for you guys on my end. Again, you know, I effed up real big, but I think we're in the right direction finally, you know, and sometimes you got to take that step in the wrong direction to figure out where the right direction is, you know?
Very good.
I don't think you effed up. I think you're on track. I mean, we're all pumping out preliminary numbers and to find out that we're way off later or we misunderstood, but it's all moving forward. You're doing great, Ben.
That's true. Thank you. Appreciate that. This has been a rocky road, but it's been a real big fun adventure, I have to say.
Yeah, well, sometimes the bad things are the best things because they teach you things that you would have never known if you just did it the right way the first time.
Yeah, that's a very good point. It's a very good point.
Yeah, oh boy, so much good stuff, so much good learning. I was poking around the comments and someone mentioned that maybe throw some salt in with the dirt. Yeah, I think that would definitely improve the conduction of the dirt. I haven't tried it though.
Yeah,
Nathan,
salt.
what do you think?
Well, yeah, salt, salinity, crystalline form, absolutely. You could throw granite in there and it would help. You got compressed quartz and anything that can create a magnetic field around quartz, which quartz has a magnetic side to it, will actually make everything amplify.
So have you tried putting a quartz rock in the center of the mud like the dirt clod?
I could put a piece of granite in 5 different bowls and hook them together with wire and get conductivity through the whole thing. Where if I just had water in there, it won't show any conductivity at all.
You should craft a granite rock into like a mini obelisk and then put it in the dirt.
That'd be cool. Yeah. So I got something John Curley's asking in the comments around about the Tesla coils I work with. So the ZBS Tesla coil resonant frequencies run between about 100 kilohertz to 300 kilohertz. And so how that's hooked up is between 12 and I would say 50 volts DC is the input to the ZBS circuit. Run with about 5 to 8 amps input. The output frequency then is between 100 kilohertz to 300 kilohertz, like I mentioned. And the voltage is 6, 7, 800 volts. It's not until the primary coil transfers that energy to the secondary coil, the Tesla coil, is where the magic happens and the voltage is stepped up to exponential rises in voltage. I hope that answers your question. Any comments or on that, Nathan?
Just took a 20K ohm resistor to your number 2 coil and set up your probes and put a how do I say this, a frequency generator to it, and then connect your oscilloscope, and it'll tell you the exact frequency of your number 2 coil. And then you base everything off of that. So every single coil will be different. So even if you tell them what it oscillates at, it won't matter because you'll have to take his own individual coil and check it. Because the Slayer Cider is forced oscillation, it'll oscillate at whatever frequency the number 2 coil is.
That's the beauty, because the number 2 coil is literally connected to the base of the MOSFET or transistor. Mm-hmm. So whatever is the perfect resonant frequency of that coil 2 is self-tuning to the base frequency of the transistor. And right. That's amazing because the ZBS, it's tough to get that close, get as close as the Slayer. But the ZBS has its positives because you can throw some pretty big plasma or try to push some higher power radiant energy than the Slayer. The Slayer has a low ceiling and what you can do with it.
Yeah, sometimes it depends on which Slayer you got.
I know yours is. Oh, that doesn't sound right. Yours Slayer is has more mass than my Slayer.
It didn't come out right, John.
I lost. Yeah, I lost that.
All right, guys, I got a video for you. Okay, I just want to show it. I showed it to the guys earlier. I'm going to show it. I was going to wait, but I'm just going to show this one. You're going to like it. So let me pull it up here.
Grab your popcorn, everybody.
One thing I will tell you about this is look at every single part because it's going to matter. We have another Tesla coil experiment. We're using our ZVS today. We're going to be at 20 volts on it. Right here we have the rod down our Tesla coil that is connected right here to this ball jar, which simply just has a piece of aluminum tape over it. The wire is not connected inside the jar. On this side, we simply have a wire shoved into the hole in the back that I drilled. And then that wire goes connected right here to this coil right here. Now, what we're going to do is I'm going to turn off the lights so that you can see this experiment very well. I'm going to show you the magnetic pinch in the second coil. So let me turn off the lights and we'll get to it. Turn that light. Now we can see the whole experiment. Tesla coil's obviously on. Our light right here lights up. We'll turn off the light just to make sure. Starts up. Goes right over our coil here. Not really much coming out this side, is there? Let's change that. Right down the center. It's the beauty of the magnetic pinch. It's creating all the forces to go into the center of it. Lights up brighter. There we go. Lights up again. We can see it gets much, much brighter in there. On the outside, there's not much going on. On the inside, it lights up brighter. Definitely an interesting setup. You can learn a lot. And yes, the glass holds capacitance. Pretty interesting. I wonder if anybody caught that. What we're going to do is I'm going to turn on. And then, so, Shawn, you there?
Yes, yes.
Now you should understand why sand is such a good thing to put in there.
That makes sense. To see basically sand in a clear form there act as, I mean, I see it as a capacitor, but you're thinking of it as more of a semiconductor.
Yes. Well, the reason it would be a semiconductor is because my frequency does not change on my Tesla coil.
Okay.
It's not going back to my Tesla coil and changing my Tesla coil itself, where normally if you hooked a bunch of stuff up, your resonance will go way out on your Tesla coil because you're adding too much capacitance, right?
Right.
So as I add that, it actually acts as a wall. So now it's cutting off my original Tesla coil from anything that comes after it. So anything that I add coming after it, I can add as much as I want and it won't change the capacitance level.
And that means it's more acting like a resistor, but it's definitely not acting like an inductor or capacitor.
No, it works on saturation. That's why I call it a semiconductor.
Yeah, so I'm sorry.
It has to saturate the glass before it can work.
So normally when the word saturation is used, it talks about transformers or a coil. For example, a flyback transformer where it has the high voltage coil around that ferrite core, and you can only run it as high as maybe 25 kilohertz. But if you run it higher than 25 kilohertz, then that ferrite core will saturate, which means it can no longer be permeable to the magnetic lines of force going through the ferrite. The ferrite just is done. It's full, can't move, can't help you, and you start losing power at higher frequencies than 25 kilohertz. Well, how are you using saturation as it relates to the glass?
So basically, you just stick two conductors on glass and it won't work. So it's not until the entire thing fills up in volume. It's like we're talking earlier, like a video game. You have full health, or
yes,
you have like no health, right? And somewhere in the middle, like the video game. So this has a full, bar right there, and it's telling you it's completely full. Now I can move on to the next level, and it can get you to your second coil. And that second coil, it's working in reverse of the first coil. It's no longer working the same way. Now I'm creating the pinch on the inside, but I have almost nothing coming on the outside, which this circuit right here, depending on the level of saturation, I can multiply the coils, pull more energy out this side as long as I have a draw. So this is where double grounding comes in. If I add a second ground at that point, it's just a suction. It'll straight suck all that energy right through that circuit real fast.
So that's fascinating. Is the saturated jar, the glass jar, is that having an amplification effect, or is it improving or decreasing the loss across the wire so you can add more across the wire?
So it acts as a resistor until you put a second ground on the other side past that Tesla coil, and then the resistance goes down. So it slows it down where it doesn't affect your first coil, but as soon as you add the ground to it, it's going to suck it right through, and then the resistance will be minimal, and then it should start affecting your primary coil.
Interesting. Are the wires on each side of the jar connected directly to the glass, or are they just suspended inside the glass?
Well, you can see it. We just shoved that little clip inside the hole that I drilled in the back. And then the front is just a piece of wire taped onto the lid.
So each side is touching the glass.
Each side is absolutely touching the glass.
Okay. Is that an important distinction?
Yeah, it has to touch the glass. It has to get in there somehow.
What if you were to put it in there without the metal part of the wire touching the glass?
It would just be the wire connected to the wire. I mean, at any distance, it would give you a volume, and then it would take the capacitance and add it to your Tesla coil. So it ruins the second Tesla coil. It'll throw off the whole resonance of the circuit.
That's a very important note, I think, because when people look at this, they thinking, oh, just throw two wires in there. No, each side has to be connected to the glass.
Mm-hmm.
That's a big point. It's something that helps me understand it.
Well, it's going to be just like your sand. It'll end up being the same experiment in the end. You'll start to find these anomalies the same way.
Oh, you're talking about when I tried to emulate your dirt experiment?
Yeah. But see, the sand reacts in the same way. You're just allowing mineral flow in the sand. You know what I mean? So it may work a little bit better where this is more altogether, it's already done.
I see. I'm working with particles of glass. You're working with a chunk of glass.
Yeah.
In effect. I still want to go get a jar from the basement and a glass jar and do this. So it sounds fun.
It drives you nuts, doesn't it? You think you get up to speed on what I'm doing, and then I change the whole game on you.
Yeah, it's funny because you always have these from left field ideas and your right curves, I guess. You're just, wait, what is he doing now? Oh, and it works. Yeah, I love it. It's part of the fringe science. Because everybody's thinking outside the box. Everybody is not afraid to challenge what we consider the conventional wisdom. And we have a lot of failure in our experiments, but we also, we lose big, but we win big, it seems like. And when we win, wow, everybody wins.
So I got to ask you, Shawn, the bucket you had yours in was plastic, right?
It was plastic. Mm-hmm.
So I just want everybody to understand that some people say when you get to the mud experiment, it was the glass, right?
Oh,
Okay, so hold on. So you don't have any glass. You have a bucket and sand.
Right, correct.
Yep.
So it's plastic. That's what I'm saying. So you took it one step further.
That for you. Yeah. He confirmed it for you. That's awesome.
That's interesting. Yeah. My goodness. Good stuff.
There's more than one way to do things, you know.
Right. Funny as I wouldn't have put it together that glass baking container full of dirt would be equivalent to my plastic container full of glass. I guess, if that makes any sense.
Well, that's why it makes sense that when you put granite inside of water and run the same experiment with plastic, glass, it doesn't matter. I do it with ceramic bowls, and it gives you conductivity through it because of the actual quartz that's being compressed inside the granite. So it should start to make sense what's going on here. We're taking crystalline form
Mm-hmm.
and we're getting the energy to produce through whatever medium is there in order to get it out.
Yeah.
So it'll act as a bit of resistance. It'll act as a bit of capacitance. It's kind of a hard thing to quantify because as soon as you put it in one box, you go, oh, well, no, it's got to go back to this box. And then, no, it's got to go back to, you're going to be doing that all day.
Yeah.
So,
you've piqued my interest. I can't wait to get back into these experiments because, good stuff.
well, you got to remember quartz is one side's magnetic and it'll pull a magnetic field around it. And as soon as it does, you're going to get capacitance. But then again, you're also going to get conductivity through the water because it's quartz. So it's kind of like there's 1,000 rules here. And since nobody does them, we don't have it written down.
Yeah, that's a good way to put it.
Yeah.
Exactly. Jabber had a really interesting point about granite, and I can't find it. Here it is. So Jabber says when you grind granite into paste, you mix it in with deionized water or other electrolytic fluids, you get a high dielectric constant with no breakdown of said dielectric capacitor. So basically capacitors with dielectrics have a breakdown, but with this granite paste and deionized water, you don't get that breakdown. That's interesting.
That's cool.
It is cool. I screenshotted it because I'm going to add that to my project list. Play around with granite because it just sounds cool. All right, we're coming up on 7:30 here, so I've got about 8 more minutes. So what do you guys feel like talking about? I'm still scouring the comments.
I need a clapper for my light switch. Yeah, it does take a while for my big butt to shuffle in there to turn it off. Yeah. Yeah. The funny thing is I put a box over here and I just never got back around to hooking it up.
No worries. So this sounds like a comment for Ben. David Gruhl, the over unity of a coil is great, but you have to first create an efficient amplifier circuit, then to calculate the power into the amp plus the volts into the coil. Not sure how to word that.
So he's saying that in order to see the efficiency gains that I want to see, I'm going to need to tweak the amplifier a little bit and do a custom circuit maybe, which is true. But we've seen that it's possible to get some kind of extra gains with the Nunez method specifically. So I think the best method is try to replicate that in its entirety and then move on to another simpler amp circuit, something that draws less power from the wall.
So hold on. So you're going to set a baseline, and then from that baseline, you're going to be able to judge how much more you're getting after that with the changes in circuit.
Exactly. Yeah. And exactly. Thank you, Nathan. Thank you. I do have something for the skeptics, and it's okay to be skeptic. I recommend being skeptic, look into this stuff. But for those who say that this is impossible, I have a quote from a man named Gerald Morin from 2014. It says, power magnification cannot be mathematically expressed by equations. Power magnification can only be expressed as a mathematical inequality. Lenz, Faraday, Newton, Maxwell's equations do not apply because algebraic equations are statements of equality. So right there, I think that kind of explains why, the math doesn't add up sometimes is because we're using the wrong math. Maybe.
Well, we're discovering new quantities and qualities that haven't been named yet. So So yeah, we're pushing past current voltage, amperage, watt,
Introducing new variables.
Well,
and yes, yeah, and new environments for these variables to show up as what hasn't yet been named.
I think it might have been named before, but Tesla's papers are missing. And I have no doubt that a man that worked with all these things knew all of this.
Yeah. Yeah, it makes sense.
So
Someone's asked, have I ever looked into geopolymers? No, I haven't. 3D Havoc. How about you guys?
Biopolymers, I've heard the phrase mentioned, but I haven't looked into it, no.
Okay.
so hold on. I'm
Sure.
gonna throw a curveball at you. When you connect an ultrasound device to a piezo buzzer, it amplifies your circuit. So one of my next tests is to take that Tesla coil as I ran it the circuit you just saw. I'm going to put it over that second coil, and I'm just going to fire it off. And I'm going to see exactly how much amplification I get out of it.
So instead of electricity to your second coil or changing magnetic field, to be exact, you're going to use the vibrational sound waves from the piezo to excite this coil 2 to output voltage.
Yes. So
wow.
What
See, I
I'm
never
gonna
even think that way.
Oh, what Tesla did. I'm gonna tell you right now. I figured out the earthquake machine, and so did a couple other people. And it's the water hammer at the bottom, it's the steam hammer at the bottom, it's the very low frequency it has at the top. The piezoelectric buzzer is going to take the effect of the water and steam hammer, and it's going to give me a pulse wave. I'm going to use that pulse wave in order to move the frequency. So it's going to basically move on sound in order to affect something else. In doing that, it amplifies the actual frequency. So if you're at 500 kilohertz, you're going to be at 1,000 kilohertz by the time I'm done pulsing it. I'm going to double my number is what I'm going to do by hitting that piezo button.
Are you doubling frequency, or are you doubling the output or input power?
You're doubling both at once. So the power and frequency go together and they spike.
Oh.
Remember, we just had Mike on here with his machine, and he's doubling his output power by using piezos.
Right. I did write down something in my notes about that. I wish I could have remembered what I wrote.
Yeah.
So just so everybody knows why I'm doing this, I couldn't get people to listen when I told them that I put the gravity flyer in the dirt and I put my Tesla coil wired right through the dirt and I used the ground as a capacitor to pull more energy. So now I have to take this Tesla coil step by step and show you every single effect. So now that you get it, I'm going to amplify the living daylights out of this thing.
Yeah. You got to test it and document everything and make sure, like, oh, that's cool. Because there's a lot of different things that you can use this for, I believe.
Oh, yeah.
I'm so on pulling out the piezo that I have, or piezo, and getting it to induce a frequency in coil 2 to see if I can get that amplification. See, that's why I love this. I love your channel, Nathan. All these good ideas keep coming out, and it's just like drinking from a fire hose. I love it.
So check it out. When I tell you about a beat frequency, what's going to happen? The piezoelectric buzzer is a receiver and a transmitter. So number one, it's going to pick up the frequency that you already have. So that's already going to be baked in. Now, when you push the button, it amplifies that to double it.
So it's a feedback loop, kind of like a microphone and a speaker.
Yep.
So Charles says, keep in mind that over Unity isn't the closed system without the benefit of an external variable, harvested energy from the aether. I believe that's what the back EMF is that we're harvesting, right?
So check it out. I can already break Unity. I can turn on every light bulb in your house with a, what, 25, 30 volt DC circuit. That's it. Give me 30 volts of DC and I can turn on every light bulb in your house.
Is that like
And
a pulsed circuit?
it's a cold electricity circuit, and I'm going to use ground to put the heat in it, and then I'm going to light up
Nice.
every single one of these bulbs.
So that makes sense, though. With everything you're discovering now with the Tesla coils, it's all coming together, really.
Yeah. Now, we haven't run a motor or anything. With light bulbs, it's pretty easy because you're exciting the gas. So it's just adding a little bit of heat. A motor might be a little bit different. So, well, we'll just see what the conversion is, because most motors are DC, and we plug them into AC. So you think they're AC. They're not. Like, your blender's a DC motor. It just, it has a conversion in it.
Right. And with the coils specifically, we've already seen that they are very efficient with lighting. So, most LEDs, I believe, require some kind of inverter or whatever to be efficient at this rate. I believe that's from what I hear. So, and this does it without it. So, I mean, we're utilizing the right energy. We're in the right realm.
I'm still stuck on that good point about how the piezo is both a speaker and a microphone, and to use it to excite or use vibrations in the coil 2 that result in an output frequency that then goes back into, I'll just say, the microphone of the piezo, and then it's output the speaker of the piezo, which is the same thing, and it creates that horrible squealing sound that you hear when people hook up their PA systems wrong. But yet here, Nathan's using it to harness basically a magnification, an increased magnification, or a runaway magnification of, I guess, power. I don't know what else to call it right now.
Well, okay. Think of it this way. You know about forced oscillation and a Slayer exciter. It's not that much different. What I'm doing is I'm forcing the amplification in the same way as the Slayer exciter forces it into the coil. It's not much different.
I'm just trying to melt the two together in my head. What I'm finding is my brain's just melting. No, this is good stuff, Nathan. Unfortunately, though, I got to head out, and it's been a great 2.5 hours with all you guys. Thank you guys in the chat. Appreciate it. Honored to be on.
This has been really, really fun. Really fun.
Thanks,
right on, guys. Thank you very much for presenting, both of you guys. I really do appreciate it. Give a hand for everybody out there. Thank you very much.
Man.
Thank you. Thanks, Shawn. Thanks, Nathan. Thanks, chat.
Thanks, guys.
All right, guys. Have a great night. I really do appreciate it.
See you next Wednesday. God bless.
Bye.